class. Okay, so what I've drawn on the board here is a something called a mass spectrometer. So, last time we were talking about the fundamentals of how a particle behaves in a magnetic field. And, one thing in particular is that magnetic fields do not do work. And so, what I've drawn here is, we'll go into the details in a minute, but we've got this beam of particles, charged particles. So we have these ions that are going to enter a region with a magnetic field. And they're going to be moving very fast. So gravity really isn't going to have any effect because they're going to be moving so fast. We don't have to worry about them falling. And say this whole thing occurs in a vacuum. And so if the only significant force acting on it is magnetic, and that doesn't do any work, then the net work done on these particles is zero. And by the work energy theorem, the kinetic energy is constant. So, the change in kinetic energy is equal to the net work done, which is zero. So the kinetic energy is constant. So they move at a constant velocity. So we have two facts to put together here. One, we have this beam of ions, and when they enter this region with a magnetic field, their path will be deflected, but the speed will remain constant. And also, this equation here gives the magnitude of the force, where theta is the angle between the velocity and the magnetic field. And in this case, the particles are moving in the plane of this board, and the magnetic field is coming out of the board. So they're perpendicular to each other. So in this case, the force is going to be QVB. And it's perpendicular. And when you have those two things, that perpendicular force and moving with a constant speed, that's uniform circular motion, which we learned back in mechanics. For an object moving in uniform circular motion, the acceleration is given by v squared over r. It's directed towards the center. So basically we have this circular arc here. And so we're going to analyze the motion of these ions, and we're going to do two parts. So what we have here, let's say we hook this up to a battery. So we have a plate here with, say, a small hole in the center. So these particles can get through, but there's an electric field in between the two plates. And these are ions, so they're positive, they don't have to be, but in this case, say we have a gas, and we just remove an electron from some of these particles. So these are positively charged ions, and so they're going to accelerate in this, basically this is a capacitor. There's an electric field between the plates, so it'll accelerate, and then once it's done accelerating, it's going to enter a region with a magnetic field. And so, we're going to analyze the acceleration part and then the magnetic field part. Now remember, potential goes from high to low. So let's say that the potential at B is 0. And the potential at A is some value. We want this potential at A to be fairly high so we can have a strong electric field and get this beam moving pretty quickly. And that's another thing I want to talk about. We talked about gases, the molecules move around with this distribution of speeds. They can be moving very quickly, but they're not all moving the same speed. Where if we have a very high accelerating potential, whatever initial velocity they had when they entered this region is going to be insignificant. We're going to get them moving very fast. So let's just say that the velocity at A equals 0. I'll write that here. Okay, now I'm actually going to write the word. So this is unfortunate notation. This is a lowercase v for velocity. But we also have VA, which is our accelerating potential. So I try to draw them in a distinctive way. It can still be a little bit confusing. So in that case, we're assuming that the velocity is effectively equal to 0. So we're going to apply conservation of energy going from A to B. So again, we're doing this whole thing in a vacuum. So we can say the energy at A is equal to the energy at B. Now we only have potential energy at point A because we're making the assumption that the velocity initially is 0, so no kinetic energy. So we have UA. Now, remember that's a lowercase VA for velocity, or sorry, we're at point B. So this would be the kinetic energy at point B, and there's no potential energy at point B. So we set the electric potential equal to 0. I guess technically we don't have to set the same potential energy and electric potential to be 0 at the same place. We'll get the same result. So we can solve for the velocity. Let's just clean this up a little bit. I'm going to write this potential energy at B. We'll get rid of it in a minute. So what I'm going to do is I'm going to move this term over here. So that'd be the velocity at point B squared. I'm going to multiply everything by 2. And then we can, this is our delta U. So this would be 2 times, remember delta U, should have written this one down. Delta U is equal to Q delta V. So the charge is, they're singly ionized particles, just by assumption. So we set it up that way. And then what we have is VA minus VB, but VB is 0. So let's put a box around this. So what we have is mass times the velocity at point B squared is equal to 2 times the charge times the electric potential at A. So again, we could just say like there's a 10,000 volt potential difference between these plates. And that'd be VA. Okay, so let's kind of stop here. And now let's look at the magnetic field. So, once it leaves the capacitor, it's moving with a constant velocity now, the electric field outside 0. And then it's going to enter this region with a magnetic field with this velocity VB. And so let's apply F equals ma. Just Newton's second law, where the only significant force acting on this particle is a magnetic force. And remember, the velocity is, it's always in the plane, regardless of where it is, what part of the motion. The magnetic field is perpendicular to the board. And so 90-degree angle, sine of theta is just 1. So the force is the electric, or the charge, which is E, times VB, times the magnetic field. And that's equal to the mass of the particle times velocity squared over r. Remember, it's moving in a constant velocity, so the it's moving at that constant velocity VB the whole time. Now let's multiply by r. We can cross off one of these velocities. So we have EBR equals MVB. And I think we're done with that. Okay. So we've set up our basic equations. One for the accelerating potential and one for when we enter the magnetic field. And now what we want to do is put these together. So what I'm going to do, I'm just going to do algebra here. So I'm going to multiply, let's start with this equation. Let's square it. We have e squared, b squared, r squared equals m squared, vb squared. And if we multiply this equation by m, we get that. So again, if we just multiply by m, we have m squared vb squared on the left side, which is this. And on the right side, we have 2m e times this accelerating potential. Okay. And ultimately, what we want to do, let's solve for the mass, actually. So we're solving for the mass, so we divide by 2e VA. And we can get a little cancellation here. Okay, so I'm going to clean this up in a minute, but let's talk about the actual experiment for a moment. Alright, so I didn't even explain this part. What we have here is a detector. So this can detect the presence of ions. Think about it. You know, these ions or charged particles are moving. This is a current. So, yeah, they're going to go into a detector. It's going to register if there's this beam of particles and how strong it is. So we have a detector there. And this detector, there's different ways you can imagine setting up this experiment. But the way we're going to set it up is this detector, everything is fixed in place. So like the ion source, the capacitor, detector, these are all fixed. We're also going to fix the potential difference between the plates of the capacitor. So VA is fixed. What we're going to do is vary the magnetic field. So in writing this equation in its final form, let's take everything else out except the magnetic field. Okay. Oh. Okay. So E is just the elementary charge. R is fixed. Say that we have it so that this beam is entering the detector. Well, even if that's not the case, no matter what the magnetic field is, like say we have a weak magnetic field, it might not have much of a circle. It's certainly not going to hit the detector in this case, but it is going to go through a very long circular arc. So it does have a radius. So, but yeah, we're really only interested when the beam hits the detector. In that case, R would just be half the distance between where the beam enters the region with the magnetic field and the region where it enters the detector. Okay, now VA, remember we fixed that. So if we get a signal in the detector, this is constant. And so again, if we have no magnetic field, let's say B starts out at 0, these particles are just going to go straight. Obviously, we will not get a signal. If we increase the magnetic field, they're going to, we'll have a magnetic force, which is causing the path to curve. And the stronger the field is, the greater this force is. So as you increase, like here, if we start with a weak field, if we start with a very weak field, it's practically going to go straight. We increase the field. Eventually, we'll get it to loop around. And then we keep increasing magnetic field, and then eventually we're going to get to the right value where we hit the detector. And so now let's imagine that we actually do this experiment. And we want to plot the signal that we get as a function of the magnetic field. Now, there's a picture in the book where you have like the signal strength. So this is a measure of like how many particles are going to enter the detector. That'd be the main factor. It would depend a little bit on the it would depend on the velocity as well. But if we have like say this is a neon gas, then the mass is relatively fixed. But anyway, so what we would expect if we were to do this experiment, the signal we should get should start out at 0 if there's no magnetic field. Basically, we should expect something that looks like this, where we either get a signal or we don't. So if the magnetic field isn't right, if we have a very weak field, we're not going to loop around enough to hit the detector. If we have a strong field, it's going to loop around and hit before it reaches the detector at all. It's not going to be a perfectly sharp spike, though, because there could be some small variations. And, maybe the detector has a finite width. So, there will be a reason that there's a little width to this spike. But basically, we either get a signal or we don't. So I might expect if we run the experiment, we get something like this. And again, I kind of copied this, can hold this up, this picture here, where that's what we actually get if we do the experiment. We get 3 spikes, and the reason why we get 3 spikes, remember, for a given mass, we can determine what magnetic field is required to hit this detector, and if our gas was, like we use this example of neon, so we have a neon gas, and if all neon atoms were identical to each other, we would just get 1 spike. They would all behave the same in this experiment. However, they're not all the same. Say we actually know the value, we do this experiment, we know what magnetic field this is, we can calculate the mass of this particle. So we measure the magnetic field, we know what E is, we know R because we're getting a signal. R is just half the distance from here to here. We measure that, we know what R is. We know our accelerating potential, so we can actually calculate the mass of this neon atom given the magnetic field where we get a signal. So what this data is telling us, if we did calculate that mass, we'd get around 20 atomic mass units. But we get these extra spikes. And if we look at this magnetic field, that would give us a signal for a mass of 21 atomic mass units. And this one here would give us the mass for an atom that has, or just any general particle that has a mass of 22 atomic mass units. And so what we've learned from doing this experiment is that the mass of all neon atoms is not the same. And we call these different isotopes of neon. Now, by definition, if it's neon, it has 10 protons. The nucleus has 10 protons. Any atom with 10 protons is neon. And, the reason we use protons is because the number of protons determines the number of electrons, because atoms want to be electrically neutral, and electrons really determine the chemical properties. So, these are all neon because they have 10 protons, but they have different number of neutrons. So this would have 10 neutrons. What we can see is some of the atoms have 11, and some atoms have 12 neutrons. So I'm not sure about the history I'm not sure if this is how isotopes were originally discovered, but it could have been how. Like if they didn't know about if they did not know about isotopes before, this experiment would have discovered them. And again, you can do this for all different types of gases and learn about different isotopes. And what's nice though, you get different signal strengths as well. Like we get a watt at 20, so the majority of neon has an atomic mass of 20 atomic mass units. That's why we get a large spike here. There's a lot of particles. So like imagine that we have the magnetic field set up at this value. It's hard to erase all this. We'll use a different color. So let's say we set the magnetic field at this value. These atoms have an atomic mass of 20 atomic mass units. They're hitting the detector. Now, some of the atoms have a larger mass. If you have an extra neutron, you have a larger mass. And so they're not as affected by the force. Or the more massive the particle is, the harder it's going to be to deflect its motion. So if we could actually see these beams, they would separate in this mass spectrometer into 3 separate beams because there's 3 different masses. So this would be like 20 atomic mass units, that would be 21, that would be 22. And then as we increase the magnetic field, this one leaves the detector, the next one enters. Then we increase it some more, and the whole pattern would shift to the left. And so it's a very nice device because it can be used not only to measure the mass of particles, but we can learn about isotopes and the percentages. Like the majority of them have an atomic mass of 20. Seems from the picture that more of them have 12 neutrons than 11. So I guess it's easier for neon to acquire 2 extra neutrons than just 1 extra neutron. Okay, so very important device here. And it's based on this idea, a very important property of magnetic fields, that the work energy theorem. Magnetic fields do no work. And so that means that these particles move with a constant velocity in this field. And it's also, the force is always perpendicular, which is, why it's not causing it to speed up or slow down. So we get uniform circular motion. And there are other examples, very important examples of uniform circular motion. I'm going to hold off on talking about another example, though, because it involves a concept we haven't gotten to yet. But there's another very important example of uniform circular motion, but we're going to have to wait a little while until we can talk about that. I guess that'll be it for this lecture. And let's see. I think next we're going to talk about magnetic torque. But that'll be it for this one.